And we're going to be talking about item 3, the electromagnetic brain burner, which is my nickname for a problem that you'll see in a few minutes. We actually started working on it last time at the end of class. But before we get to all that stuff, I want to go through a few announcements. Anyways, month of November quotations are from Will Rogers, kind of a famous guy, interesting guy. He was born in the late 1800s, I guess, very popular during the Great Depression, so 1930s. He started out as a cowboy in Oklahoma and then became a performing cowboy on stage and a humorist and became a writer and actually became a star in Hollywood in the 1930s. And very funny guy. And like this quote, ancient Rome declined because it had a Senate. Now, what's going to happen to us with both a House and a Senate? And kind of a humorous guy, and he poked a lot of fun at the government. And it's nice to mention it in these days because we got this big election on and everything, and everybody's all. But it's always everybody's concerned about this is happening and that is happening and ain't it awful? But really, there have been people, poking fun at the government for a long time, and he was one of the most famous ones in our history, anyways. We'll be seeing a few quotes from him this month. Reading and topics rough schedule page is updated. I had a student ask me last week for it. I got to it yesterday morning. We'll look at it in just a second. Sign-ups for special study groups. If you're not one of the special study group leaders, then you can sign up. By the way, if you're a special study group leader and you have not turned in your printout, you are not going to be a special study group leader because I have to have this signed and in my hand. And if you don't give me this signed and in my hand as soon as you can, then you're going to have to take the final exam. So you definitely want to do that. Anyways, Monday night, you guys will be able to sign up at 7 p.m. Now, I want you to write that down and put big stars next to it and sparklies if you have any of those in your book bag and whatnot. Because at 7 o'clock p.m. on Monday night, it is going to be a Buffalo Stampede to get spots because we never have enough for everybody to get in. All right? So you've got to be ready. And I predict that by about 7:05, all the spots are going to be full. Now, it might not happen that way, but that's what I'm going to predict. It might be 7:06. I might be a little bit off. But it's going to happen. And so you want to be ready for that. So there's a special sign-ups page in Web Courses. Now, it's not accessible for you guys yet. We're working on it, and it will appear at 7 p.m. Monday. It'll appear as a link on the schedule page. Now, the way that this works this semester is a little bit different. We used to divide the class up into the students that had the lowest grades on average and then everybody else, and let the people sign up early that had the lowest grades, and then after a couple hours, let everybody else. But we're going to do it just every man for himself, every man and every woman for himself or herself. And just first come, first serve. So expect, just try not to get trampled in the Buffalo Stampede. So check the SSG schedule page that you can now look at. Now, it's under construction. And what you want to do is look it over and see if there's a couple, 3 SSG sessions that fit your schedule. And if you can do that, if you don't get in, if you get in there at 7:02, 2 of your 3 groups might be full already, but the third one might not be. So be ready to make decisions. Okay. Also, if you sign up, think very carefully about what you sign up for. Because if you sign up and you don't go, you don't get any bonus points. And 2, you're going to be on my you-know-what list because you're taking a spot away from somebody that does want to go. And every semester, I talk to students, and they always say, Dr. B, I just couldn't get in there. I got stuck in traffic or my job or, any number of reasons. They want to go there. And if you take a spot and they can't go and you don't go, oh my goodness. And I'm going to know who you are too, because we'll be able to know who's participating in SSG. So don't let that be you. You be a person that is thoughtful. Sign up for what you know you can make it. And the schedule, you'll see it in a minute here, is there for you to look at for that purpose. Now, attendance and participation in the special study groups is going to earn you 4 bonus points, and hopefully it will allow you to perform a few points or more higher on the exam as well. So that alone is nice, and then you get 4 bonus points. So hopefully this will have a beneficial effect on your grade. And so if you can get it, good. If you don't get it, it's not going to hurt your grade, and you can still study. And I always tell students, find a study partner or a study group. And I know a bunch of you guys are studying together, and that's good. And I talk with people in office hours. Darien has office hours at 1 p.m. on Mondays in the Physical Sciences building in the atrium. And studying with another human being is sometimes a really good... Like yesterday, we were talking about... What were we talking about? Oh, the convection brain burner. And the one that we were, you have capital P subscript CD and capital P subscript CV and capital P subscript R. And how is it that convection is dominant? And we talked a lot about that, and the students that were mystified by it got a better handle on it because we talked about it together. And that is what studying can help you to do. It can help you, Lacey, to think. And thinking is what I want every single person in here to be able to do every day of your life, and especially on exam day, because that's how you're going to crush it. Now, here's what the rough schedule of topics and readings is, and I don't know if you guys have looked at that. I filled in week 9 through 12, and I'll try to get week 13 and on out after the exam. But just so you know, here's the basic stuff of the last 2 weeks anyways. Lecture meeting 24 is going to be the midterm, and I've changed that because of the hurricane. I had it set to chapters 7 through 10, but actually we're going to be doing chapters 6 through 9. And you can look at the rest of the schedule page, the rough schedule of topics and readings, to get the exact parts of chapter 6, 7, 8, and 9. And we're going to be talking about chapter 8 today and pretty much finish it up. Although we're going to be practicing with the chapter 8 topics that we're going to tackle today. And next week, lecture 23, next Tuesday, we're actually going to be talking about the atoms. So we're stepping up the mountain. We're walking up the mountain, getting closer and closer to the periodic table. We're almost at it. Now, the sign-ups page is going to look like this. There's a big red stapler and a picture of the TAs. Here's the, what do you call it, the link. That's where the link is going to be. So at 7 p.m. on Monday night, you want to be on this page so that at 7 o'clock and 1 second, you can click on the link that's going to be right there. Right now, there's no link, so you can't get to the sign-ups area. We're working on the sign-ups area, and at 7 o'clock on Monday night, you'll click there, and then you'll see the sign-up things, and you'll be able to click to sign up. Okay, so you special study group leaders, You do not select the people in your group. The people in your group select you. They look at your schedule on the schedule page, and then they decide, yep, I want to go to that one. All right? And so you just never know. We'll do this again on the way to the final exam in finals week, and it will work in a similar way. Special study group leaders, you'll be able to set up a different time, place, location, etc., and you'll have a different set of 6 students, potentially. So it is, it works in that way. Now, down below that link area, here's Chelsea and a bunch of other students, their pictures, and their meeting times and stuff. Now, Chelsea's are not up yet. She hasn't told me what hers are, but you can look in there right now and see a few people have got their data in there. And hopefully, by the time Monday night at 7 o'clock rolls around, everybody who's told me yes, they want to be an SSG leader will have their times and places figured out. Question in the back. What?
Sorry if I missed it, but did you say how many spots are going to be available?
How many? I didn't say how many spots specifically, but every group. See, I don't know how many groups we're going to have, but every group is going to have 6 students and the SSG leader. All right. So if we have 10 groups that activate, that's going to be 60. All right. That's about 1/9 of the enrollment in the 2 sections. If we have 20 groups, which potentially we do, that'll be about 120 students. And so that'll be, like a fifth, between a fifth and a fourth of the class. So it just depends. But per group basis, 6. And so let me reinforce that your job for the next few days until Monday night is to scope out the SSG schedule page and find a few sessions, 2 or 3 that, yeah, I can make that for sure. I don't want you to make a note or join a session that you can't go to, okay? And stuff happens. Like you get in a car accident or your roommate is arrested for, being a nuisance or whatever. And, you can't make it, but you've got to be very careful and ultra paranoid about joining groups that you can make. All right? So be ready to click into that. It works really nice. You'll be able to click in and then, ching, you're in. And then you SSG leaders, I'll give you a PDF file that you print out, and that'll be your attendance sheet. And you'll get the students to sign in on that, and then you give that to me, and part 1 is done. And then you'll do it again finals week, and you'll hand it to me during my office hours or at the final if you want, and you'll be able to skip the final. So you've got to do it twice. Now, special admonition to all you SSG leaders. I do not want you to have any more than 6 people in your group other than you. I don't want you to go around being a nice guy. Oh, yeah, come on, you can come in. I don't want that. I don't want you to be overburdened, so keep it at the 6 that you get. You're going to probably all have 6. If you have a friend that couldn't get into your group, study with them after your group is done. Your group is a 60-minute session, small but helpful. 6 students, small group, but they're going to be very grateful for your help. All right? But don't, Caroline, the other TA for the second lecture, she, and I know some of you other guys have had study groups going a long time this semester already. You guys are free to do whatever you want. But in the SSG session itself, 6 for 60 minutes, and keep it at that. Keep it simple. KISS. Keep it simple, student. Keep it simple, SSG leader. All right, last time we talked about phase space. This abstract space in which we represent sometimes the entire dynamic range or the entire motion of a system. And the one that we studied was the oscillating system. And two of the landmarks are listed. The top of this ellipse for an oscillating system is 0, p max, maximum momentum. Maximum rightward because it's above. And then over here on the far right, that's x max, 0. That would be maximum rightward motion, or the limit, the turning point of the rightward motion. And so we looked at that last time. And for an oscillator without friction, it works out to a perfect ellipse. By the way, make a side note, a perfect circle is also an ellipse. It's a special case of an ellipse that is as wide as it is tall. But no matter what the dimensions of the ellipse, it's a good representation, and there's a huge amount of information encoded in that. Now, that's for an oscillating system. Free fall, as I alluded to last time, looks completely different, and we're going to take a peek at that and then a clicker question about it. So have your clicker out, have a little bit of iced tea if you feel like it, and get your clicker ready, and let's take a look at the phase space representation of an object in free fall. So here it is. Go ahead and make a sketch if you like. The vertical axis is the y component of the momentum in kilogram meters per second. And the horizontal axis is the coordinate y. It's always the component of the momentum and the corresponding coordinate. So y component and then corresponding y coordinate on the horizontal usually. All right, and it goes from 50 to minus 50 in my graph. I mean, but you can see that the states follow a way different curve. It is not an ellipse. This is a free fall phase diagram. And this one, it goes from negative 100 meters to 0 out to 100 meters in the y dimension. Now I'm going to ask you a question about this, so I'll get your clicker ready, and we're set up here. And I'm going to give you the diagram back in just a minute. And this is going to be something I want you to think really carefully about. It is not an easy question. So talk to your neighbors. I'll give you a good amount of time to think it over. Describe the motion based on the visual inspection of the phase diagram. Now, we know it's free fall, and all 5 descriptions there have some kind of a motion. Right? So read those over. And here's the diagram itself. I'll give you a bigger version of it in just a second so you can look at it. But first, read those. Let's see how this works out. I bet we'll get a lot of this. Yeah. All right, now if you want, here's a bigger version of the diagram. Okay, so you can improve your sketch of it in your notes if you need to. And I'll go back to the options in just a second. All right. So just re-verify your diagram. And this is just a bigger version of the one that is in the question itself. Okay, let's get back to those options. Go ahead and vote. A, B, C, D, or E. I'm very interested to see. And definitely talk it over with your neighbor. Does this make sense? I think this is good. Et cetera, et cetera. What?
It went out.
No, it's... Can I have some vitamin water? Thank you. This green tea / vitamin water. Try to stay hydrated up. What do we got? 16. 30 seconds. Good one, Dr. B.
Yeah, you got it on the mic.
Nice. It was really full. Well, now my mic is hydrated up.
I don't know if mics are supposed to be hydrated.
I'm pretty sure they're not supposed to be hydrated, but we got 2 backup units over there. Unbelievable. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Very interesting. I see you guys still talking it over. That's good. Well, I love to see you guys doing that. Starts at maximum y, then moves left. There's no left in this. This is the y coordinate. It's either up or down. There's no left or right. A is out. 11% of you chose A. Remember, this, if you chose A, write down, this is not a picture. It's not a photograph or a simulated strobe photo of a set of positions. This is an abstract graph. So the left side of this diagram doesn't mean left side of the classroom or anything else. All right? So A is out. Falling straight down, acquiring more and more downward momentum. Downward momentum is the left side, or excuse me, downward momentum is the bottom half of this phase diagram. And it's getting further and further down there. All right, at each second. And those dots, by the way, my wonderful students, are 1 second apart. And you know what this is? This is, I got a minus 1/2 GT squared in here. That's it. And a minus GT for the speed behind the spreadsheet that generated this graph. So falling straight down, ching. But wait, let's look at the other options. It's like a baseball pop-up, heading straight up and then straight down. No. There's no heading straight up in this one, because there's no momentum state represented in the upper half. So a few of you chose that, but make a note of it. There's no state represented in the upper half, so nothing upward. That's where all the upward momentum is. You know, positive y momentum means you got a little bit of kilogram meters per second going upwards. All right? So C is out. D, it moves left to right if S. Left to right, no way. That's x-axis. Those are x-axis adjectives. It is launched. What? 32% of you voted for E? Is that right? It is launched upward from about level y equals minus 20, and then it slows down and stops, like being caught by a baseball player at y equals 100 meters. How come it, why do you say it stopped? I mean, I'm just curious. I mean, whoever voted for this, tell me why you think it stopped. Raise your hand and tell me why. Or die in the attempt of telling me why. Why do you think it stopped? Right, well, that's what this says. It stops at y equals 100. So why do you think it stops? What does the what on the graph suggests to you that it is stopped at y equals 100? The momentum is 0. Okay, the y component of the momentum is 0, so actually, those of you that voted for this, you're correct too. And I want you to write down both answers to this because there's something fundamental I want to point out to you. B and E are both correct. But the direction of time is different. Time is moving from right down to the left for option B. But time is moving from the bottom of the chart up towards the middle right of the chart in option E. The phase diagram can tell you the direction of time itself. So if you know that one set of points is after the other, then you know which one is. That would eliminate one of these options. So if I told you that this dot down here at negative 20, y equals negative 20, approximately. If I told you that that was the initial momentum state and position, then you'd say, okay, I know the direction of time because I know it goes up to the right. But if I told you that this one over here is the initial momentum state, 0, then you have something that's dropped from a certain height, 100 meters. All right? And so the direction of time is, and that is also true. Oh, my students, we're getting down to some good stuff here. The direction of time can also be represented on the ellipse for an oscillating system. Now, one thing I want to tell you about here for the oscillating system that we studied last time, the ellipse, it's fairly easy to calculate the area of an ellipse. The circumference is really tough. Circle is not too hard. Circumference of a circle, area of a circle, pi r squared for the area, 2 pi r for the circumference. Ellipse, the area is simply half of the width times half of the height, okay, times pi. That's it. Now, in common mathematical parlance, usually this distance, this is half the width, and they call that if the width is the longest dimension, the biggest dimension, this is called the semi-major axis. Symbol is usually the letter A. And this one, half of the height, that's the semi-minor axis for this ellipse. So half the height, half the width, multiplied by pi, and that is the area. Let me park this up here a little bit to the right and upwards. Yeah, those are the dimensions of the ellipse. And if you think about it, this corresponds to the area of a circle if you realize that for a circle, A and B are equal. And they're known as the radius of the circle. This formula becomes pi r squared if A and B are equal and replaced by the symbol r. Okay, so dynamically speaking, now in terms of our dynamical ellipse in phase space, the area is equal to pi times maximum x, that's this coordinate out here, times maximum momentum, that's this y coordinate up, or this vertical coordinate up here. But what is the dynamical interpretation of area? I mean, we know the area, the units are angular momentum or action. But what does that area represent? And my wonderful students, there's a fundamental mystery in the area of the ellipse here relating to time itself. So this phase diagram, it's very, very interesting. And I'll just leave it as an open question for you for the present time. By the end of the semester, I'll give you more about that interpretation. So let's go back to the forces on nearby charged neighbors that we were talking about last time. We had, I think, an electron and then 2 protons, and I asked you, what's the direction of the net force? That was the last question that we asked last time. We're going to start working on that, and this is all that we're going to work on today. The reason is we want to figure out molecules, and this is the kind of exercise these nearest neighbor and extended arrays of charges will help us figure out some of the factors in simple molecules. Water has a molecular shape that looks like this. It has what we call polarized structures. So that means the hydrogens are kind of tilted out into like a wide letter V, a wide triangle. And so it turns out that the electron that orbits the hydrogen is pulled or bonding with the oxygen atom, and therefore the side of the hydrogen, I made it a little bit blue on the side facing, I don't know if you can tell, I guess you can. Wow. Oh my goodness, this looks black over here. The left side of the hydrogen, oh my goodness, definitely look at this in YouTube. This left side of hydrogen is does that look red to you, where my cursor is? Okay, I can't really see that. Maybe it's just my angle. And then over here on the right side of this hydrogen atom is supposed to be blue because that's where the electron is going to be between the oxygen and the hydrogen. And that means the positive end of the molecules is the H or hydrogen end. And the oxygen side of the molecule is going to be negatory. And the angle that the hydrogens make, we know that very, very precisely. It's 104.4776 degrees. So it's a little bit more than a right angle, 14.4776 degrees bigger. So don't make that a right angle. Make it an obtuse angle. All right? So like a pretty wide V. All right? We also know the distances. From hydrogen to oxygen, it's about 0.0958 nanometers. And when I said the other day that nanometers were the usual or handier units for studying atoms and molecules and stuff, this is what I mean. Okay? In scientific notation, that'd be about 9.58 times 10 to the minus 11. Now, all this stuff you can figure out by understanding the Coulomb interaction and doing a little bit of F equals ma and some trig and etc., a little bit of calculus and stuff. All right, so this water molecule is just a fairly simple molecule, very abundant here on Earth most of the time, except in the Sahara Desert and places like that. But the DNA molecule is extremely complex. It's enormous. And there's intermediate sized molecules as well. Proteins are pretty big. But we all try to model them based on the stuff that we're going to work on today. Now, the other thing that we talked about last time was the Coulomb interaction. And as you know, the Coulomb interaction is an inverse R² force. We use the equation K times Q1 times Q2 over R². Q1 being the amount of electric charge on an object, Q2 being the amount of electric charge on the other pair. It's a pairwise interaction, so we think of one charge interacting with another charge, And then we look at another, if there's more than one charge in the area, then we tackle that next charge. And then we tackle another charge, however many charges we have. And that's what we're going to be doing today. Try to work it out carefully. R is the distance between the two. Remember my code, this one looks a little more red. My visual code is red for positive charges, blue for negatory charges. Okay? And let me just rotate this line segment. Here's R down here. There's the distance. So that's a separate parameter. The closer you are, the stronger. When R is small, the denominator is small. And so the quotient itself, the total quotient for F, is larger. So as R gets smaller, the force itself gets bigger. Now, I have some more questions for you about interaction forces. And hopefully this is a basic one that you can answer carefully. And it's using the same diagram, Q1 being positive, Q2 being negative. Here we go. Which pair of force arrows is correct? If Q1 is positive, Q2 is negative. Pair 1, pair 2, or neither? "30 seconds. I haven't had any Ricola for a while. Yeah.
I've been fighting off getting sick for the past few years.
Dude, no wonder you're sleeping in. You need sleep. Sleep is going to... Boy, you're getting low on Ricolas. No, you better use them all. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, most of you got it right. Very good. Pair number 2. And the reason, go ahead and make a sketch if you like. And just remember, pair 2, Q1 and Q2 are opposite charges. Or they're opposite sign. One's positive, Q1, one's negative. So they're going to attract each other. When you're studying molecules and doing the brain burner that we're going to be working on today, you have to keep this factor in mind. Are the two charges that you're studying, Katrina, are they attracting or are they repelling? It's a significant issue, and you've got to get it straight in your mind. All right, next question. Separation D is equal between the protons and between the electron and the middle proton. Okay, so that's this distance D, and then over here D. If the proton-proton interaction is 40 micronewtons, how large is the electron-proton interaction? By the way, micro means a millionth. It's abbreviated with the Greek letter mu, and it's the same as 10 to the minus 6. So, but we could just talk in terms of micronewtons. Go ahead and vote for whichever one you think is good. 10 seconds. 10, 9. Wait a minute, I'll give you a few more seconds. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And we have trouble because 43% of you voted for A, 48% of you voted for B, and neither of those are correct. Option C is the correct, so you better make notes. And I'm ready for you. I want to go over this with you. It's 1/4 of the nearest neighbor interaction. So the two red protons on the left, they have 40 micronewtons. And my answer, 10 micronewtons, is a fourth of that nearest neighbor force. So that's the force between proton and proton in this diagram. Okay, some other diagram you might have a different force, a different pair of particles. But in this one, the two nearest neighbors are the for the target particle that we're thinking of, which is the rightmost particle, is proton-proton. So now here's the given information. The force between the protons is 40. Right? Now, 40 micronewtons. Now we're going to work with that number. We're not going to work with the constant K, the Coulomb constant, 9 times 10 to the 9, etc., etc. Although we could, but we're going to work with just this figure here. We're going to leverage the Coulomb interaction formula, K times E in the numerator and D squared in the denominator. Go ahead and write that down. That's just applying the given situation that we have, E being the charge on the proton, and we got two of them. And so what I'm saying, and here's an abbreviation for it, K times E squared over D squared. And hey, you guys, I just thought of something. Do you have a pen? Can you give me that pen? You know, I've been spending a lot of time thinking about that phase space diagram for the oscillator. So my mind is, no, that's not right. That's interesting. Okay, good. Just had to write down a thought that came to my mind. Anyways, here's the given information, 40 micronewtons. And if you plug all the symbols in that we have, that's how you'd represent it symbolically. Now, I haven't told you what the distance is, but you can figure out the distance and then you plug it in and work out to 40 micronewtons. Now, let's do the electron-proton interaction. And this is the interaction between the electron and the proton on the right. All right? So my target particle that I'm trying to figure out in this problem is the proton on the right. And so my electron is twice as far. So look at the denominator. It's 2D quantity squared inside those brackets. That is where the difference comes. The numerator is a minus E for the electron, and then over here, a regular E for the proton. All right. Now, in terms of the formula, I'm just kind of doing a little bit of algebra. That's the same as minus KE squared. Notice the numerator is the same. But the denominator, when you square the quantity 2D, you get 4D squared, and that's the new denominator. Right? The minus sign, notice I've parked my minus sign out in front. Now that minus sign means that the force is in the opposite direction. All right? And that's how we encode repel and attract. Now normally we won't worry about that. We'll kind of use words to describe the directions. But if you were working with the formula, yeah, that's how the directionality would come up. So the proton gets a rightward push from its nearest neighbor, the middle proton, and it gets a little bit of leftward pull, opposite direction, from the electron. Now this quantity over here, minus KE squared over 4D squared, that's actually the same as, go ahead and write this one down, minus 1/4 times the quotient KE squared over D squared. And that is not a coincidence. That's the same as minus 1/4 times the proton-proton force. And that is why 10 micronewtons is the answer. At least that's the size of the force. If I was asking about direction, and we're going to need to know directions, you would say leftward or rightward, depending on the situation, depending on the geometry of the array. Question? What's that?
Can you go back to the question real quick?
Sure. There's the question. All right. So here's the nearest neighbor. Here's the target particle. We're focused on this one. The nearest neighbor is this. The second neighbor is this. It's twice as far away, so the force is 1/4 as strong. All right? So let's keep going here. Yeah.
What did you get? Why is it 2D squared?
Because it's twice as far away. Did you make a sketch of the array? Yeah. Here it is again. There's the array. Okay, so my target particle is this baby. I'm asking about the forces, Evangeline, on this one, on the far right. All right? So the electron is twice as far away because it's 2D away. That's why I have this, here's one D and here's another D. All right? Pay attention to what I'm about to say. The problems that we're working on today, you're always going to have evenly spaced electrons and protons. Right now in nature, they're not going to be evenly spaced. But for us, this is like doing a workout in the gym. You do squats so that you can run the 100 meters. You don't go to the Olympics to do squats. You go to the Olympics to run 100 meters. Okay? And so this is going to be like a workout. But in real life, doing the 100 meters, or in real life doing a real atom and stuff, the distances are not going to be the same. But for us, this is a good workout. Okay? All right, so there we go. 40 micronewtons. K E squared over D squared. And then the other force, K minus E squared over 4D squared. And that's minus 1/4, opposite direction, and 1/4 of the size. All right. Now, in general, let's write down the general principle here. Question?
So if it was like 4 away, then you would put a 4 instead of a 2?
No. Yeah, that's right. And then what's 4 squared?
2.
4 squared is equal to 2?
Oh, no.
What's 4 squared? Yeah, so if you're 4 times as far away, it's a 16th of the size. Okay, and that's what we're getting to in this slide. All right. So in general, you've got this inverse R squared force, and that is what you want to study in this type of a problem, the electromagnetic brain burner. So if you have only electrons and protons, Evangeline, the charges are the same size. And if you say that they're equally spaced, D, and then another D, and then another D, then the second neighbor out, in that case the electron, is 1/4 of the nearest neighbor force. And hey, you guys, I frequently use N and F as a symbol or an abbreviation, an acronym for nearest neighbor force. NN for nearest neighbor, and 2N for second neighbor, which in that question before was the electron. Here's the target particle. You always have to identify your target particle. Which one are you trying to find the forces on? I'm interested in the rightmost proton in this problem. Now, if I have some other problem, I can deal with another particle. But for this problem, this is my target. Here's my nearest neighbor. Okay, in this case, it's a proton. But in another problem, it might be an electron or something like that. But we're not going to have nuclei. We're not going to have minus 2e or plus 4e or anything like that. It's just going to be plus e or minus e, protons and electrons. And then we got this. Now here's my generic neighbor out here, a distance nd away. But if you triple the distance, okay, then in the denominator you have 3d quantity squared. What's 3 squared? 9. And so you got 1/9 of the force. And then, of course, at that point, you also have to decide, well, is it a leftward force or is it a rightward force? And to decide that, you have to know if it's an attraction or a repulsion. So you've got a lot of decisions to make, and you got to make them pair by pair. All right? So let's talk about the nth neighbor. In general, for this kind of evenly spaced array of protons and or electrons, the nth neighbor, n times as far from the target particle as the nearest neighbor, the interaction force is exactly 1/n of the nearest neighbor force. So if I say the nearest neighbor force is 40, then let's see, the fourth neighbor is 1/6. What's 1/16 of 40? 40 divided by 16 is 2.5. So if the nearest neighbor force is 40 micronewtons, the fourth neighbor force would be 2.5 newtons. And it might be left or right depending on if it's a repulsion or attraction. So that's the general principle in these problems. Now, if you have 7e and negative 3e, you got to do things a little differently. But if our numerator is always the same, so Oscar, if we go pair by pair and we're only taking electrons and or protons, my numerator is always going to be a ke squared and maybe a minus sign in front. And then the only thing that changes is the denominator, d squared, 2d quantity squared, 3d quantity squared, 40, and on up to however many neighbors you have. Right now, we're going to work on this together, and just to reinforce, we're trying to figure out molecules and what molecules do. And a real molecule is a lot tougher to work on. It's not evenly spaced, maybe, and the mass of the proton is way bigger than the mass of the electron. But this is a good workout for us. Here's a kind of a strategy map. If you know the nearest neighbor force, and if you know the distance ratios, right? So if they're evenly spaced, you have distance 1, distance 2, distance 3, distance, as many neighbors as you got. If you have those two, then you can figure out the net force. So if I tell you the nearest neighbor force is 111 skillion 203 newtons, then you can figure, and you know the distances of all the others, you can figure out the net on your target particle, right? So let's do a problem together, and we're just going to go step by step. Now this is going to be a bigger array. All right, so let's do this carefully together, and keep your clicker ready because we're going to be doing some more questions here in just a minute. Okay, so here's in general my electromagnetic force is K times E times a minus E over R squared, or maybe K times E, or K times minus E, depending on what you got. Goes pair by pair. And let's say that the nearest neighbor interaction force is 288 nanonewtons, right? And that gives us a toehold to figure out all the other interaction forces for all the more distant neighbors. So if I set the force scale at 288 nanonewtons, you can get all the other neighbor, so many nanonewtons for each of the other ones. And you can figure out the directions if you know the signs and so forth. All right? So, now my target particle is the leftmost electron. So put a question mark next to this to indicate this is my target, or indicate that it's the target particle. We're trying to find the net force on this baby. All right. Now my nearest neighbor distance is right here. I don't have it specified, but I do have the second neighbor distance, and that's this dotted line segment. And what I'm saying is that it is twice the nearest neighbor distance. In other words, 2D. All right? So, as we already know, the electron to electron repulsion is going to be a fourth of my nearest neighbor force. Okay? So my starting point is an array of charges like this, a target particle to consider and study, get the net force, and then some information about the nearest neighbor force, in this case, 288 nanonewtons. Okay? Now that means whatever my nearest neighbor force is, I divide that by 4, and that's the size of my second neighbor force. All right, so I've got this baby, and let's do some arrows here. Here's my baseline nearest neighbor force. I put a dot up there to represent the target electron. The repulsion force is to the left, and its size is 72. 288 divided by 4. Better get your calculators out. You're going to need them. Just have them handy. And it's a repulsion. And the reason for that, this target particle here gets a leftward shove from this second neighbor. The second neighbor is over here to the right. It's an electron. So the effect on that is going to be 72 nanonewtons to the left. Right? So now I got this second neighbor squared away. All right, and we're still working with the nearest neighbor interaction, 288 nanonewtons. So let's get the pull force now from the second proton. All right? That's this one right here, the second proton from the left. Second proton from my target particle. All right, let's work on that one. Now, here's my distance line segment. All right, up here, this dotted line. And let me park this out of the way. That distance line segment out to my third neighbor, in this case a proton, that's 3 times the nearest neighbor distance, so 3D. All right, 3D quantity squared is 9D squared. So my factor is 1/9 of the size of my nearest neighbor. So 1/9 of 288 is my electron to proton attraction. Because remember, my target particle is an electron, negatory, and this particle, this is the third neighbor particle. It's a proton, so it's going to try to pull the electron to the right. Now, 288 times 1/9 is 32. So for my third neighbor interaction, I get a plus 32 nanonewtons. All right? And that's the third neighbor attraction force. Right? So you have to figure out the size. You have to figure out, okay, is it an attraction or is it a repulsion? And then once you figure out if it's attraction or repulsion, then you have to decide, okay, which direction is that going to, is it going to push to the left or is it going to pull to the right or vice versa? So you have a lot of decisions to make. You've got to work through it carefully. All right, so now we have this guy squared away. All right. So we could add all these together if we wanted to, but we still have one more neighbor to square away. And that's that last proton out there to the right. All right, I've got 4 neighbors. This is neighbor number 4, that last proton. All right. What's my shrink down factor going to be? Fourth neighbor out. It's 1/16. All right, so let's work that out. So there's my distance line segment. And this is going to be the weakest pull force on the target electron. And it's 4 times the baseline distance of the nearest neighbor. Okay, so that's a 4D in the denominator. So the shrink down or the weakness factor is 1/16. All right. Now I happen to choose 288 because I know that 288 also divides with 16 in a nice way. So 288 divided by 16 is 18. It's pretty nice. All right. So that means, all right, this is a proton acting on an electron, and that's going to draw the electron toward the proton. So that means it's going to be a little bit of rightward, not too much. And hey, you guys, these arrows are accurately drawn. I was real careful about making sure each arrow here was the same or the proper length, all proportional. So I have 3 rightwards and 1 leftward. Right? So my last particle is squared away. Right? And so there's my set. Now, I want you to write down a vocabulary term. These are the 4 constituent forces on the target particle. Okay? They constitute, when you put them all together, the net force. So the terminology I like to use is constituent forces. Okay? You've got 4 neighbors. You've got 4 different constituent forces to figure out. And you're going to get it by the time exam 3 rolls around. You're going to be crushing this. But what we got to do now is just add them up. All right, so 266. Add up the positives, subtract the negatory. And you know, if I give you a different problem, like for instance, if I ask you about the rightmost proton, you might have a completely different force, set of constituent forces, and different net force. Okay, so you just got to work it out. Question? The negative 72 is from the second neighbor, which is an electron. That's this baby. Second neighbor out, shrink down factor 1/4. 288 divided by 4, 72. And it's leftward. It's pushing the target particle to the left.
The target particle is the...
It's the leftmost baby. Yeah, that's the one I told you. Put a little question mark over that or next to it. All right, so my net electric force is 266 nanonewtons. All right. Now, we're going to, for the last 10 minutes or so, we're going to work on a problem step by step together and do a slightly different set. I think it's different. Okay, this is a different set. All right, so get ready to make another diagram and another set of arrows, and we're going to do some more decisions. And we're going to do that on your calculator. All right, so make a sketch. And here's the preamble, you guys, for all the questions that are to come. Make your sketch. And we're going to focus on the leftmost electron, but now my other neighbors are different. I've got a proton for my nearest neighbor, nearest to the target particle. And then I got 2 electrons. That's neighbor 2 and neighbor 3. And then neighbor 4, way out there, is a proton. So I got 2 protons and 2 electrons affecting my target electron. All right. And also, on homework that you're going to have over the weekend, I'm going to fry your brain with this stuff. I mean, it's just, you're going to, it's going to be rough. You're going to be, but I'll try to give you plenty of attempts. I'm always going to give you the nearest neighbor force. And in this case, it's 576. All right. Now, I'm going to give you different arrays, different number of neighbors, and different nearest neighbor force. But once you get the array, and the nearest neighbor force, you can do everything else. All right, here's one of the questions that you have to ask. The force of the leftmost proton on the leftmost, so the force of this guy, nearest neighbor, on the leftmost electron, that's this guy, is, which of those four? Go ahead and make sure you make it. I see some people going like this and over like this. And that's good. 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 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, 44% of you chose A, and A is correct. 39% of you chose B. Now, this is a common place to make an error. You realize that a proton and electron are going to attract each other, Samantha. All right? But then you still have to decide, all right, what direction is that force going to be? So you've got to know attraction or repulsion and which direction it's going to be. So in this case, the force on that leftmost electron is toward the proton. In other words, rightward. Right. Force of the center electron on the leftmost electron. Next question. Okay, go ahead and hopefully you guys get this one better. Okay, electron and electron. And we're not talking about sizes yet. We're just trying to figure out directionality. And because when you're doing this, left would be a negative number of nanonewtons, whatever it happens to be, and rightward would be positive. So you got to get that. If you don't do that, your sum's not going to work out right. Okay, so we're just getting directions here. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, where's my... Okay. So this electron and this electron, they're going to repel. So it's got to be either C or D. All right? Now, this electron here is going to repel away from the other electron. That means leftward. And guess what? 64% of you chose that, which means you're learning. I got you right where I want you. All right, so let's take a look at what we got here. All right, we got some leftward. We got some rightward. We still have to figure out the sizes of each of those. And then also we got to figure out size and direction for these two. So we got two more neighbors to tackle. And actually we have, okay, see you later. We have 4 sizes that we've got to tackle. All right? All right, let's go to the leftmost electron, our target, and the rightmost proton. Let me start this question. Since Darian had the bolt. Now we're talking about the SIZE. 576. Let's see. 1, 2, 3. Okay, that's the 4th neighbor out. 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Oh my goodness. 60% of you got this one right. Yeah, 576 divided by, if you got that one wrong, it's 576. Fourth neighbor out. Shrink down factor is 16th. So 576 divided by 16 is 36. All right. You're dismissed. Homework 14, brain burners. Oh my goodness. Be ready for special study group sign-ups on Monday night. Special study group leaders, come on up here and talk to me for just a minute.